NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve a Diophantine-style equation built from floor functions. We will follow a clean, algebraic algorithm and finish with a complete description of all solutions. We are given the equation, floor of x plus floor of y plus the product of floor of x and floor of y equals k, where k is an integer. We will denote floor of x by left floor x right floor, and floor of y by left floor y right floor, and we will derive a formula for the integer floors first, then translate them back to intervals for x and y. Rewrite using m equals floor x and n equals floor y. The equation becomes m plus n equals k. Now isolate the terms with m on the left. Factor the left side. M times the quantity 1 plus n equals k minus n. Before dividing, we must check the special case when 1 plus n equals 0. If 1 plus n equals 0, then n equals negative 1. Plugging back into m times 0 equals k minus negative 1 gives 0 equals k plus 1. So k must be negative 1. Therefore, if k equals negative 1, any real x works, and y must satisfy floor of y equals negative 1, that is y in the interval bracket negative 1, 0 parenthesis. Now consider the general case when 1 plus n is not 0. We can divide both sides by 1 plus n to solve for m. Next, apply a simple algebraic manipulation mirroring the algorithm. Add and subtract 1 in the numerator and reorganize to expose a clean split. Now, since m is an integer, the fraction must be an integer. Therefore, 1 plus n must divide k plus 1. This is the key divisibility condition. Finally, translate back from m and n to x and y. If m equals floor x and n equals floor y, then x is in the interval bracket m comma m plus 1 parenthesis, and y is in the interval bracket n comma n plus 1 parenthesis. Let us collect everything into a neat solution template. Case 1, k equals negative 1, gives solutions for any x with y in the interval bracket negative 1, 0 parenthesis. Case 2, for k not equal to negative 1, choose any divisor d, positive or negative, of k plus 1. Set n equals d minus 1, and m equals negative 1 plus k plus 1 over d. Then x lies in bracket m comma m plus 1 parenthesis, and y lies in bracket n comma n plus 1 parenthesis. Let us illustrate with a concrete example. Suppose k equals 5. Then k plus 1 equals 6. The divisors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. We will pick two sample divisors to generate explicit solution intervals. First, choose d equals 3. Then n equals d minus 1 equals 2, and m equals negative 1 plus 6 over 3 equals 1. So x lies in bracket 1 comma 2 parenthesis, and y lies in bracket 2 comma 3 parenthesis. Next, choose d equals negative 2. Then n equals d minus 1 equals negative 3, and m equals negative 1 plus 6 over negative 2 equals negative 4. Therefore, x lies in bracket negative 4 comma negative 3 parenthesis, and y lies in bracket negative 3 comma negative 2 parenthesis. Recap. Factor the equation in the floors, handle the special case when 1 plus n equals 0, and otherwise use the divisibility condition that 1 plus n divides k plus 1. Each divisor produces one integer pair for the floors, and thus one rectangle of continuous solutions for x and y. That completes the solution. In this lesson, we will solve a classic floor function equation using an elegant factoring insight, and then we will list every solution set clearly. The equation is open bracket x close bracket plus open bracket y close bracket plus open bracket x close bracket times open bracket y close bracket equals 7. Step 1. The key idea is to add 1 on both sides, and then factor. We write open bracket x close bracket plus open bracket y close bracket plus open bracket x close bracket open bracket y close bracket plus 1 equals 8. Now factor the left side as open bracket x close bracket plus 1 times open bracket y close bracket plus 1 equals 8. From here we can isolate open bracket x close bracket as minus 1 plus 8 divided by 1 plus open bracket y close bracket. because open bracket x close bracket and open bracket y close bracket are integers, 1 plus open bracket y close bracket must be an integer divisor of 8. The divisors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. For each choice of 1 plus open bracket y close bracket equals d, we get 1 plus open bracket x close bracket equals 8 over d, and therefore the intervals for x and y follow from their floor values. Let us work one full example to see the mechanics clearly. Suppose 1 plus open bracket y close bracket equals -2. Then open bracket y close bracket equals -3. So y is in the interval from -3 to less than -2. Using our formula, open bracket x close bracket equals minus 1 plus 8 divided by 1 plus open bracket y close bracket, which is minus 1 plus 8 over -2, that equals -5. Therefore, x is between -5 and less than -4. Now, we will enumerate all 8 divisor cases to get every solution pair of intervals. For each d in the set plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, we compute open bracket y close bracket equals d minus 1, open bracket x close bracket equals 8 over d minus 1, and then turn those into the corresponding x and y intervals. To build intuition, let's also view these solutions on an xy plane as 8 shaded unit rectangles. Each rectangle corresponds to one pair of floor values, and therefore one interval for x and one interval for y. Watch as we place each rectangle for all 8 divisor cases. Summary: the factoring identity turns the equation into open bracket x close bracket plus 1 times open bracket y close bracket plus 1 equals 8. Since the left side is a product of integers, we let 1 plus open bracket y close bracket be a plus 1 times open bracket y close bracket plus 1 equals 8. Since the left side is a product of integers, we let 1 plus open bracket y close bracket be a divisor of 8. Each divisor gives unique floor values and therefore a unique rectangle of solutions in the xy plane. These 8 rectangles together describe the complete solution set to the equation. In this lesson, we will solve the equation with floor functions, open bracket x close bracket plus open bracket y close bracket plus the product open bracket x close bracket times open bracket y close bracket equals -1. We will follow a clear algorithmic path. Isolate the floor of x, consider the special case when 1 plus the floor of y equals 0, and then describe the full solution set visually and symbolically. Step 1. Let capital A be the floor of x, and let capital B be the floor of y. Because floors are integers, a and b are integers. The equation becomes a plus b plus a times b equals -1. Step 2. Following the structure, isolate the floor of x. Move terms to get open bracket x close bracket times quantity 1 plus open bracket y close bracket equals -1 minus open bracket y close bracket. Then write the highlighted template with k equals -1. Floor of x equals -1 plus k plus 1 over 1 plus floor of y. Since k is -1, k plus 1 is 0. Step 3. Case 1. If 1 plus the floor of y is not 0, then the fraction is 0, so the floor of x equals -1. That means x lies between -1 inclusive and 0 exclusive. Substitute floor of x equals -1 back into the original. We get -1 plus floor of y minus floor of y equals -1, which simplifies to 0 equals 0. This identity holds for any floor of y when it is not -1. So, for case 1, all x in the interval -1 to 0 correspond to any y whose floor is not -1. Step 4. Case 2. If 1 plus the floor of y equals 0, then the floor of y equals -1. Plugging that into the original equation gives floor of x minus 1 minus floor of x equals -1, which is always true. So, in case 2, y must be in the interval -1 to 0, and x can be any real number. Let us visualize the solution set with number lines. On the x-line, the interval from -1 to 0 is shaded, showing all possible x from case 1. On the y-line, the interval from -1 to 0 is shaded, showing all possible y from case 2. The full solution set is the union of two rectangles in the xy plane x in -1 to 0 with any y, or any x with y in -1 to 0. Final collection. Summarizing all cases. Either the floor of x equals -1, which means x is between -1 and 0, with any real y whose floor is not -1. Or the floor of y equals -1, which means y is between -1 and 0 with any real x. Equivalently, the solution set is the union, all pairs with x in -1 to 0, any y, union any x with y in -1 to 0. There are infinitely many solutions. Quick check. With a equal the floor of x and b equal the floor of y, add 1 to both sides of a plus b plus a b equals -1 to get a plus 1 times b plus 1 equals 0. Therefore, a equals -1 or b equals -1, which matches our two cases exactly. Final answer. All ordered pairs x, y such that x is in the interval -1 to 0 with any y, or any x with y in the interval -1 to 0. In this lesson, we solve a special type of floor equation using a clean algebraic trick. We'll follow the exact algorithm, rearrange, check the integer condition, and then note several useful variations. Let's begin. Here is the general equation. We will treat the floor of ax and the floor of b, y as integers and factor cleverly. Step 1. Let m be floor of ax and n be floor of by. Then our equation becomes m plus n equals k. Now add 1 to both sides and factor the left. The quantity m plus 1 times n plus 1 equals k plus 1. Solving for m gives m equals -1 plus k plus 1 over n plus 1. Substituting back, floor of ax equals -1 plus k plus 1 over 1 plus floor of by. Step 2. For a solution to exist, the right side must be an integer because floor of ax is always an integer. Therefore, k plus 1 divided by 1 plus floor of by must be an integer. That is the required divisibility condition. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.